Yeah, so as I was saying, we can look at some other nucleophiles. So if we look at, for example, hydroxide, let me keep with the same. Let's say I'm looking at hydroxide down here. Okay, that's a pretty small nucleophile, but I can change it and make it a slightly less good nucleophile by adding a methyl group to it. Okay, so I've replaced the hydrogen with a methyl. Still, still a good nucleophile. It's just not as good as OH minus. Now I can start playing with it even more. Now it's becoming not such a good nucleophile. Right, now we're getting a lot of steric bulk on this alkoxide. And then finally, the one that we use a lot of times when we want to avoid SN2 altogether. Is Tert Butoxide. Okay? So again, in terms of favoring SN2, this is just a different series of nucleophiles. And the real takeaway here is that the smaller the nucleophile, right, the better it is going to be as a nucleophile, generally speaking, and the more it's going to favor SN2. And sometimes this is not really relevant, like if you're trying to look at bromide versus iodide. Okay, yeah, one is bigger than the other, but there's not really a steric issue with these that I would worry about too much. Why would one be better than the other? Generally, when you're talking about sterics, you're talking about the substitution around it. So if you come back up here and look at this isopropyl group that we have hanging off of this, we're worried about all these carbon atoms that are sticking off of there. That's what really adds to that's what we're talking about usually when we're talking about sterics. And the same thing for this amines up here, right? This is a tertiary. It's got 3 different substituents on its tertiary amine, so it's worse than, say, a primary amine. And it's important, even though I know it's confusing. It's important to realize that this is a scale, right? The bigger ones don't favor SN2. It doesn't necessarily mean they won't do SN2. It just means that it becomes less and less easy to do SN2 as it gets bigger, and we kind of look at some of those. The hardest cases are where you started getting on the border between is it going to go SN2 or is it going to go SN1? But these are the main things that we want to consider when we're considering whether or not something's going to be SN2. So we would want to look at these 3 things primarily. There's also solvent effects. And I'll just say it because I don't want to get into the thermodynamics of it because it's confusing. The last thing, the smallest thing to worry about is that these are favored by polar. Well, actually, I'll just save that for a whole different lecture because I have to explain what some different solvents are. So for now, this is fine. The solvent thing is a small piece. All right, let's now look at SN1. So for SN1 mechanisms, we're not concerned with sterics. Okay? Sterics, not an issue. It's complicated. I guess what I would say for SN1 is, let's look at it from this. They're favored by electrophiles that can form stable carbocations. Okay. And we kind of talked about that, right? If you're going to form a stable carbocation, you're going to, so I'm trying to keep my colors consistent. So yeah, green, we're talking about electrophiles. So yeah, favored by electrophiles that can form stable carbocations. Let's just start there. So remember, our first step is to kick out the leaving group And so this carbocation is going to be a lot easier to form than this carbocation. Okay? So this is so slow that it doesn't even really happen. Never observed. Let's see, what's the other thing here? Also, they're favored by bad nucleophiles. Favored by bad nucleophiles. So what types of things typically do SN1? Well, it's going to be things like water or alcohols, or maybe some sort of like carboxylic acid, like acetic acid or something like that. But generally, these things are favored by bad nucleophiles, and so that it's a harder it's harder to explain what. So in SN2, those things are favored by good nucleophiles because good nucleophiles that are not sterically hindered, because the reaction itself is faster. It's faster when things are not sterically hindered. With SN1, it's favored by bad nucleophiles, but it's not like the bad nucleophiles. The reason for that is that the nucleophile itself is not involved in the rate determining step. So remember, the first thing that has to happen here is this has to pop off, and then I have to form a carbocation. So a bad nucleophile like water is just this really stable entity without a lot of electron density that it really wants to give up. It's pretty happy being water. Doesn't really need to form new bonds or anything. And so by virtue of kind of not being a good nucleophile, it gives the substrate time to sort of eject its leaving group. So in an example where you have a really good nucleophile, the good nucleophile may participate in the first step. And if it does, then you're not going through SN1 anymore, you're going through SN2. So SN1 and SN2, now we'll start getting into, so let me spell this out. Bad nucleophiles are unreactive. And allow enough time for the leaving group to depart the electrophile. I'm just going to abbreviate electrophile. And we'll revisit that. Okay, so let's pit these two things against each other then. So when do we observe SN2 and when do we observe SN1? So if you go into the book, the textbook, there's a flow chart at the end of the chapter. Chapter, I forget which one it is, 9 maybe. But whatever the one is on substitution and elimination, it will guide you through how to decide whether something goes SN2, SN1, and then ultimately we're going to get to E1 and E2. But you can follow this kind of set of heuristics to get to the right answer, right? And I have full confidence in your ability to do that. More important is kind of understanding, at least to me, what's more important is understanding why that's true. Why is it true that you can kind of follow this flow chart? How are we making the decisions at each intersection of this flow chart? but I'll give you some idea of what you can expect from these things. So SN2, you'll see it with methyl. If we're looking at electrophiles, it's favored by methyl in primary. Okay. It can do secondary, but we never see tertiary SN2. So if your electrophile is tertiary, we never, ever, ever see it go SN2. Okay? So if you see something like it doesn't matter what your nucleophile is, you can have a great nucleophile. This is never going to go, never SN2. It doesn't mean a reaction won't happen necessarily. It just means that it's not going to go SN2. In this particular case, you'd see, we're going to call it no reaction or some extremely slow reaction. So if you like the Klein workbook, I know some of you have it. It's what is it called? Organic Chemistry as a Second Language. Be really careful with that one because the way that Klein looks at these is slightly different from the way that Anson and Iverson, those guys, look at this. And we're going to use the Anson kind of lens to look at this. So trust the Anson book for this, even though I know it's a little harder to learn out of. It's technically more correct. And so, we're going to go with that over the way that Klein explains it. So here we're going to say this is never SN2, it's no reaction, or it's such a slow reaction that it's not practically useful. SN1, so right now we're just looking at the difference between electrophiles for, we're looking at the difference between electrophiles for SN1 and SN2 reactions and how they sort of reinforce each other or don't. For SN1, it's favored by tertiary. So in this case over here, we'd say like favors SN2. Tertiary, that's not going to happen for us. For SN1, we see sort of the opposite. We see a tertiary being favorable, secondary, sometimes you'll see it, primary, and methyl never do SN1. So these are the nice ones to hold on to. Okay? And so if you're just looking at a reaction and you know it actually goes, let's say that there is an actual reaction that happens, and you're trying to decide between SN2 and SN1, if it's primary or methyl, you know it has to be SN2 because that never happens for SN1. And if it's tertiary, then it's not going to be SN2, it's definitely going to be SN1. Okay? So the trends sort of reinforce each other in opposite directions. As we'll see when you get to elimination, there are other things we have to worry about this other set of... So there's, in total, things can go through, for substitution elimination, they can go through SN2 and SN1, and then E1 and E2. So there's 4 different mechanisms that are all sort of in competition with each other. Okay? So the way we're used to kind of looking at reactions is, this is a reaction, this is its mechanism. The reality of most reactions is there are multiple different types of mechanisms that are competing, and in this chapter we're looking at some of the more important and well-studied ones for substitution elimination and saying, okay, well, how do they compete, and how can we say what's going to win in a competition? So let's look at an example here. or some examples. If you go to page 85 in your workbook, which we're not there yet, you're not there yet, they have a ton of examples in there, and I strongly recommend working towards that once we get through elimination. But yeah, let's look at let's start out with some straightforward ones. So if we're looking at these two reactions, and let's say that I'm saying like predict, the question might say like, predict the products and name the mechanism. In our case, this is either SN1 or SN2. Okay, this is what your analysis would look like. You'd come in and you'd say, okay, what's my electrophile? Your first step is what is your electrophile and what is your nucleophile? So our electrophile is this in both cases. It's very unusual for an electrophile to have a negative charge, so if you're confused about which one it could be, it's definitely not the one with a negative charge. But yeah, so that's our electrophile, and then like, what are our nucleophiles? Our nucleophiles are going to be these species. And so now we need to figure out, are we going to expect these to go SN1 or SN2? And then what are the products going to look like? So let's assume, this is not always true, but let's assume that we actually get the substitution reaction to happen. What we would have up here is this. Okay. Our leaving group would be Br minus. And then down here, our substitution product, this would be a little bit weirder because it's water. So you might be tempted to draw out this, but that would have a charge on it, and we just don't see that. I'm not going to form that. We'll actually form, just like when we looked at this for the alkene chapter, we don't form the protonated species. We actually just form an alcohol. And then again, our leaving group is just going to be Br minus, or HBr if you want to draw that out. It doesn't really matter. Okay, so I don't necessarily, if I know it's a substitution, I don't necessarily need to know if it goes through SN1 or SN2. But yeah, we can still say which one it is. So what the analysis that I'd go through is first look at the electrophile. So we're going to start at the top one. We're going to look at the electrophile. What's our electrophile? It's primary. Okay? What do we say about SN2? SN2 is favored by primary. Okay? And what about SN1, which would be competing with SN2? SN1 never, and you can even still see it in the screen, SN1 never, ever happens on a primary. And that's because a primary carbocation is just too high in energy. So what's our mechanism here? Just by looking at the electrophile, we can say it's SN2. Further things that support it's going to be SN2 is that we have a good nucleophile. Cyanide's a good nucleophile. But we didn't even have to really go that far. We could say it just right away. Okay? So good nucleophile, primary electrophile, definitely going to go through SN2. We come down to this second example, we look at our electrophile, that's going to be tertiary. Okay, so what do we know about tertiary? Well, if we look at SN2s, we know that SN2 never happens for tertiary, and we know that SN1 is favored for tertiary. So this favors SN1, and then we can come over and even look at our nucleophile and say, well, what about the nucleophile? Is it a good or a bad nucleophile? And it's a bad nucleophile, which also favors SN1. Okay? And so that's more or less what the analysis typically looks like when you're going through these things and you're trying to figure out which mechanism is actually happening. Is it going to go SN2 or SN1 or E2 and E1 ultimately when we get there? You're looking at the electrophile and then you're looking at the nucleophile and you're just making some judgment calls about what it supports. Okay, and these are straightforward situations. When you get to secondary, so remember that both SN1 and SN2 can happen on a secondary substrate. So in the previous examples, in the previous two examples, if you just looked at the electrophile, you could make a judgment call on whether it was going to go SN2 or SN1, assuming a reaction happened. Now I'm looking at something that's secondary. And so for a secondary, it could be SN2 or it could be SN1. Okay, so that doesn't really help us that much here. And so what we need to look at in this case is the nucleophile. So if the nucleophile is good, let's say we use cyanide again, or why don't we get some variety here. Let's use let's just use iodide to displace it. How about that? So if the nucleophile is good, that's going to favor SN2. Doesn't matter, we don't see it in the product anyway, but we'll see some situations like if we kick in stereochemistry, we'll be able to see if it does in fact affect the products in those situations. And a lot of the workbook problems have that in there. We're just kind of easing into it right now. All right, but what happens if we use a bad nucleophile? Let's take a look at that. So again, it's secondary, so is it SN1 or SN2? We don't know just from looking at the electrophile. We have no idea just looking at that. But if we have so we use an alcohol over here for our nucleophile. Now we've got a bad nucleophile, and now things go SN1. And again, be careful when you're drawing this on that you don't put the proton on here. So you'll notice that the proton here does not appear in the product. That gets stripped off. And the same is true over here on the water. That proton does not appear in the product. So when you're using alcohol, when you're using bad nucleophiles that don't have a charge on them, they should not stay protonated on the product. And you can convince yourself of that by walking through the mechanism. Okay, so this is SN1 versus SN2, more or less in a nutshell. First thing I usually look at is the electrophile. The electrophile restricts SN2 and SN1. So you're never going to see an SN1 if it's primary, you're never going to see an SN2 if it's tertiary. So if I have either of those cases, I can at least eliminate some possibilities. If that doesn't help me, then I have to go to the nucleophile. And that's what we did in the second set down here. These were slightly harder because secondary, well, who knows what it's going to be? Is it going to be SN2 or SN1? I don't know. But if I come and look at my two nucleophiles, that helps me decide. So for secondary substrates, you have to look at the nucleophile. You don't really know which way it's going to go. And we'll see when we get to eliminations that it gets a little bit more complex than that. Okay, we'll look at some other examples in the next set. Yeah, we'll look at some other things to consider in our next example, and I'll go into like really crazy detail on the mechanism for SN2 and SN1 and show kind of how these two things are competing together.